Today's lesson is on ionization trends and how we can use the trends in ionization energy to prove the existence of sublevels. So for today's think and answer, what does the word trend mean? The word trend can mean a pattern, and that can be useful because you can use a pattern to predict things, right? You can use information you know to identify a pattern and then use that pattern to predict further information based on that. So after today's lesson, you should be able to understand how trends in first ionization across the period um, will account for the existence of main energy levels and sublevels within atoms, right? So main energy levels are 1, 2, 3, 4. Sublevels are S, T, D, F. You'll also see how successive ionization energy data for an element gives information that shows a relationship to the electron configuration for the element. And you should be able to figure out what group an element is in based on seeing its successive ionization energy data. You should be able to explain the trends and any gaps in the data in the trends um, across the period. Okay, so here we see a graph of ionization energy for an element, right? So this is what we call successive ionization energies, right? So this is for aluminum because it has a atomic number 13. Successive as in this is the energy for removing the first electron, then for the second, third, fourth, so on and so forth. So if we look at this, we can kind of figure out a pattern. Right? We see first that there's an increase. Overall, there's an increase. As you go from the first ionization to second to third, there's an increase. But the first three are valence electrons that are the easiest to remove. These are the three that require the least energy to remove since they're on the outer shell. But each one requires a little bit more energy than the last. If you remove the first electron, right, you've taken your neutral aluminum and turned it into a positively charged aluminum ion. Now this positively charged ion holds its electrons more strongly, requiring slightly bit more energy to remove that electron. And the third one takes slightly more energy to remove. All right, and then we see a little gap from a little bit of a jump, right? It's not a steady increase anymore. There's a greater jump between 3 and 4. Why is that? Because this fourth electron is in the second energy level. It's not on the third level like the previous ones were, right? This is closer to the nucleus. It's more tightly held on. Also, this is a full shell. This full shell is pretty stable and it doesn't want to break up the group. The 8 wants to stay 8. So it takes a significant jump in energy to remove that electron. Right, so these next electrons are removed from the second level. So as you keep going, you need more and more energy to remove these successive electrons and continue ionizing aluminum. Now, once these 8 electrons have been removed, we see a significant jump again. Why? Because now to remove any further electrons, now you have to move them from the first energy level, right? From n equals 1, which is the closest to the nucleus, the most tightly held on, and requires the most energy to remove. So that is the pattern. Whenever you see a sudden jump in the increase of ionization energy, that probably means you are now removing an electron from a lower energy level. Right, so again, there is always a successive increase in ionization energy. The second electron always takes more energy than the first, the third even more. This is because as your atom becomes more and more positive, there's an increasing attraction for the electrons that are remaining, and it requires more energy to remove them. When you see jumps, that is because you are now trying to remove electrons from a full shell, right? A shell is considered full if it has 8 electrons. So the second energy level, after you remove these first 3, the second energy level is considered full. to remove anything will be decreasing the stability, which doesn't happen unless you provide an extra amount of energy. And then we can break this information down further. So these first three were from the third energy level, but we see here, even within this little piece here, there are slight irregularities because this first electron comes from 3p, sublevel 3p, which is slightly higher in energy than sublevel 3s. So since this electron is already higher in energy, you don't need to add that much more to remove it. 3s is slightly lower in energy, so you have to add just a little bit more energy to remove electrons from 3s. Right, then we see this large jump because now we're trying to remove this electron here from a shell that's full. And another jump here because you're trying to remove an electron from the first energy level, which is filled by 2 electrons. And a closer look at the second level of aluminum, right? If we look at the second level of aluminum, the second shell has 8 electrons, 6 of which are in 2p, and the last 2 are in 2s. So we know that 2s is lower in energy than 2p, meaning if something is starting from a lower point, to get it to leave the electron, you have to add more energy to it. If something is starting from a slightly higher level of energy to start with, you don't have to add as much to get it to that convergence limit and remove it from the atom. Okay, here is what the electron configurations would look like for these ions, for these successive ions. This is the full electron configuration for aluminum. When it gets ionized, the first one is removed from P, right? Because that's the outer level. The next one is removed from 3s. The next one is removed from 3s, leaving just the first and second shells full, right? And now that the first and second shell is full, we would expect a jump in ionization energy to take this electron off because this configuration is particularly stable. Okay, so there are trends also in the ionization energy as you go across a period or as you go down a family. So when you look at the periodic table, as you go across a period, your atomic number increases, right? As you go from left to right, your atomic number goes up. Hydrogen has atomic number 1, helium has atomic number 2. The higher atomic number, the more your number of protons, the more your nuclear charge, the more strongly electrons are held on to the atom. And so the greater the ionization energy you need to put in to take that electron off, right? So more protons as you go across the period, higher ionization energy. As you go down a group, your number of energy levels increases, right? The first period has 1 energy level, the second has 2, the third has 3. So as you go down a group, your valence electrons are further and further away from the nucleus. And they're shielded from the nucleus because there's more electrons between that outside electron and the nucleus that's holding on to it. So as your atom gets bigger, as there's more energy levels, your electrons you're on the outside are easily removed. So your ionization energy decreases as you go down. So those are the 2 general trends, right? Ionization increases as you go across and it decreases as you go down. But there are some discontinuities. But those discontinuities are regular in a way and can provide us with information that shows the existence of sublevels. So here, this is the first ionization energy of some atoms graphed against the atomic number, right? So as we go across this graph, we can just see as the ionization energy increases or decreases for a particular element. So hydrogen has a very low ionization energy, right? Relatively low, so that means the electron is removed relatively easy. Helium has a very high ionization energy. What that means is it's very stable. It'll take a lot of energy to change it. It'll take a lot of energy to take that electron off. It's happy how it is, right? So helium is not likely to change. It's not likely to be ionized. Lithium, though, it only takes 500 kilojoules per mole to ionize lithium. So lithium is very ready to lose its electron, right? So anything you see with a high ionization energy like helium, neon, argon, those are these noble gases over here. They are stable. They are happy to stay as they are. They do not want to lose their electrons. Anything with a low ionization energy, like hydrogen, lithium, sodium, aluminum, potassium, right? These are all over here. These have very low ionization energy, meaning they will readily give up their electrons. It only takes a little bit of energy to take their electrons from them. All right, so as you go across a period, the general rule is your ionization energy will climb, right? So hydrogen to helium, it climbs. Let me draw. So hydrogen to helium, that's overall, you see ionization energy increasing. Lithium to neon, that's in the second row, right? Overall, you see the general trend is ionization energy increases. Same thing for sodium to argon, right? This is period 1, 2, 3. You can see those right here. Period 1 is for the first row, 2 is the second row, 3 is the third row. So as you go across the rows, and generally they climb. But what are these zigzags? Why isn't this a continuous trend? Because of a couple of peculiarities. So we see here lithium, sodium, potassium, right? They're the lowest because it takes, they only have one valence electron. And it's very easy to remove that one valence electron, because if you take away that electron that's on the outer level, it will reveal a full octet of electrons in the level right underneath, which is stable. So the reason lithium, sodium, and potassium are so easily ionized is because they produce ions that are particularly stable. Now let's look at boron, aluminum, and potassium. Boron and aluminum right over here, right? Why are they so easily ionized? Boron would theoretically have a higher ionization than beryllium if we followed the trend, but it doesn't. What that means is beryllium is ready to lose its electron in a way. Because if beryllium loses its electron, it has one electron in the p orbital, right? In beryllium has 2 electrons in 2s and 1 electron in 2p. If you empty out the electron in 2p, then beryllium is just left with 2s, which is a full subshell, right? Then 2s is full and p is empty. 2p is empty. That's particularly stable. So beryllium is happy to do that. Same thing for aluminum, which is in the same family, right? It has 2 electrons in the 3s subshell and 1 electron in the 3p subshell. So if the 3p gets cleared out, you're just left with a full 3s subshell, which is stable. So aluminum will readily lose its electron, so it can become that stable aluminum ion. Next, we see oxygen and sulfur also have a dip in ionization energy. Instead of sulfur having a higher IE than phosphorus, it's lower. Why? So remember what we said earlier about full subshells being particularly stable, but also half full subshells being particularly stable. So sulfur, or let's look at oxygen first. Oxygen has 2 electrons in 2s and 4 electrons in 2p. So 2p can fit 6, right? If 2p is full, it will have 6 electrons. If 2p, which is stable. And if 2p is half full, it will have 3 electrons, which is also particularly stable. So out of the 4 electrons that are in 2p for oxygen, if you lose 1, you'll have 3 left in 2p, which is also particularly stable. So oxygen will readily lose its electron. So instead of having 4 electrons in 3p, it'll have 3, which is half full, which is happy. It's stable. It wants to do that. Same thing with sulfur. Sulfur has 4 electrons in its 3p sublevel. So it'll toss one, right? Let something else take it away, and it'll be left with 3 in its p sublevel, which is also stable. And so that explains like sudden dips in energy level, right? Drops that you don't expect. What explains sudden jumps that you don't expect? A sudden jump indicates something that's already stable, right? So let's look at beryllium and magnesium. These both have sudden jumps. That means this already has a S sublevel that's full. It's good how it is. It doesn't want to change that much, right? So it will take slightly more energy to ionize it. Same thing with nitrogen and phosphorus, right? We see there's jumps here. Because nitrogen and phosphorus already have 3 electrons in the p sublevel, you need just a little bit more than usual energy to change it because it doesn't want to change, right? So the trend is, if something can become stable by losing an electron, it will have lower than expected ionization energy. If something is already stable because it has a half full shell or a full shell, then it's going to have a slightly higher than expected ionization energy because it's reluctant to change. All right, so some practice problems. In period 2, there is a decrease in first ionization energies between beryllium and boron. And then in period 3, there's a decrease between magnesium and aluminum. How do you explain this decrease in ionization energies between group 2 and group 13 elements? So let's look at our periodic table. All right, so let's look at beryllium and boron. So just as a reminder, everything in this first family, there's 1 electron in the s orbital, right? So hydrogen, there's 1 electron and 1 s. Lithium, there's 1 electron and 2 s. Everything in this family has 2 electrons in the s orbital. So beryllium has 2 electrons in 2s. And then here, this is your p block, right? So everything in this column has 1 electron in the p sublevel, 2 electrons in p, 3 electrons in p, 4, 5, 6 electrons in p. That's the pattern. So beryllium has how many? It's got 2. It ends its electron configuration in 2s2, right? Because it's in the second row, and s2 because it's in the second column. Boron, its configuration ends in 2s2, and then it's got 1 extra electron, so that's 2p1. So between these two, which one is more stable? Something is more stable if it already has an orbital that's half full or full. So beryllium has a full s sublevel because s fills with 2 electrons, p fills with 6 electrons. So this one's not full. This one is full. So beryllium is slightly more stable as it is. So beryllium is going to have a higher ionization energy, and boron will have a lower ionization energy for that reason. And you could also consider it as boron, if it loses this, if boron loses this electron, it's going to be like beryllium. It's going to have a half full s sublevel, and it's going to be more stable that way. So boron will easily lose that last electron, so it can be stable like beryllium, right? So if it loses this, it's going to have the same exact electron configuration as beryllium. All right, so formal explanation. The group 2 elements have the electron configuration ns2, n as in whatever energy level it's in, right? So beryllium is in energy level 2, so 2s2. Group 13 elements have the configuration ns2, np1. So boron is in group 2, so 2s2, 2p1. The electron removed when the group 13 elements are ionized is a p electron, right? So this one is a p electron. When the electron is removed from the group 2 element, it's a s electron. So electrons in the p orbital are of higher energy and they're further away than the s electrons, and so are easier to remove than electrons in an s orbital. So I'm realizing now that that is a completely different explanation from what I just verbally said to you, but both of those explanations are valid. Okay, so next question. In period 2, there is a decrease in first ionization energy between nitrogen and oxygen. In period 3, there's a similar decrease between phosphorus and sulfur. Explain the decrease. Right, between group 15 elements and group 16 elements. These are group 15, these are group 16. So how does that work? So we can tell right away that this group is more stable, right? So it's going to have a higher ionization energy. This group, if it loses one of these electrons, will become like this. It will become stable, right? So this one is happy to change, meaning it'll have lower ionization energy. So to formalize that, group 15 elements have the electron configuration NS2, NPX1, NPY1, NPZ1. So actually, this is a different explanation from what I just gave you. So let me show you what that means. What that means is there's 2 electrons in this s orbital. There's 1 electron in the 2px orbital, 1 in the 2py orbital, and 1 in the 2pz orbital. Remember, there's 3 p orbitals. If I draw them out, it's going to look like this. This is pz, this is px, this is py. So each of these, instead of these 3 electrons being doubled up anywhere, each of these have 1 electron. Those electrons are distributed amongst the 3 orbitals, right? But if we look at oxygen, there's 1 additional electron, so that 1 additional electron has to double up. So not only is this nitrogen stable because it has a half full sublevel, it's also more stable because there isn't this extra repulsion between electrons in the same orbital, right? In nitrogen, each electron is in its own orbital, but in oxygen, one of these orbitals contain 2 electrons, so there's a repulsion there, which creates instability, which means this electron over here is easily removed, and there's a lower ionization energy. All right, next question. The 4th ionization energy of vanadium, which is right here, is 46,000 kilojoules per mole. And the 5th ionization of vanadium is more. It's 6,280 kilojoules per mole. And the 6th ionization energy is a huge jump to 12,400 kilojoules per mole. Right, so if I were to visualize it, it would be like this. And then this one's a little bit higher. And the third one is way higher, right? So there's a jump here. And it says, explain why the 5th ionization energy for vanadium is higher than the 4th, right? So why? Simple reason. There's always a successive increase in ionization energy. The second is higher than the first, third is higher than the second, fourth is higher than the third, and so on and so forth. All right, next question. Explain why the difference between the 5th and 6th ionization energies is much larger than the difference between the 4th and 5th ionization energies. So let me draw what I had again. Right, so this is your little axes, right? Ionization energy increases that way. Your 5th, your 6th is a little bit higher, and then your 7th is, 4th, 5th, and then your 6th is way higher, right? Because you went from 400 to 600 to double. So why is it so much bigger? So let's look. So vanadium, right, is right over here. So the first electron that you take away is the third one in D. Then you take away, oh wait, I'm mistaken. Okay, so why does that happen? So we can see here, this is the first, second, third, fourth, fifth, right? So the fourth and fifth electrons are in 4s. The sixth electron is in 3p, right? So imagine your convergence is here, right? This is where n equals infinity. This is where the electron has to jump to leave, to produce an ion, right? To escape the atom. So for an electron to leave from 4s, it has to jump this much, right? You need that much energy. The 4s electron already has energy up to here, so you need to bridge the gap to get to here. So that's what your ionization energy is for an electron to escape from 4s. But for an electron to escape from 3p, 3p is significantly closer to the nucleus, and it's lower in energy. So you're starting at a lower energy point. So to get to that convergence limit, you have to put in significantly more energy for that electron to be removed. All right, so fourth and fifth electrons are both removed from the 4s orbitals. The sixth electron has to be removed from 3p, which has a lower energy orbital, and so is held closer and more strongly to the nucleus. Okay, couple of multiple choice. Right? So the first ionization energies of a particular element are 732, 1450, blah, blah, blah. What I like to do for these is kind of like draw the dots, kind of to visualize. So let's draw this. So I'm just going to place 732 at some random place, right? Then I see 1450 is about double that, okay. Then I see 7730 is not a double anymore, it's a big jump. So whatever that third one is, there's a big jump. And then, right. So this is my rough plotting of the 4 ionization energies. So now I have to figure out what group number the element is in. How do I know that? By seeing how many electrons are taken away before there's a big jump, right? However many electrons are taken away before there's a big jump, that's how many valence electrons there are. So there's 2 electrons before the big jump. That's 2 valence electrons. That means it's in group number 2. Okay, same thing for the second question, right? So we'll do this again. Draw it out. It helps to visualize this, to draw it. 590, okay, this looks like it's about double that. That looks about right. Then this jump, that's not double anymore. That's like triple. So that's a jump. Right, so here we see again our jump is after the second electron. So again, this is going to be something in group 2. And of these elements, only calcium is in group 2. So when you're given successive ionization energies for an element, to figure out what element it is, you just have to see where the jumps are. And based on that, you know how many valence electrons it has. And based on how many valence electrons it has, you know which group it's in. And you can identify the element. All right. Here, successive ionization energies for carbon, they're listed out. Why is there a large increase between fourth and fifth? So let's look at the periodic table. Right, here's carbon. So the first ionization energy takes off an electron from P. The second one takes off the second electron from P. Third one from here, fourth one from here. So that just cleared out the second energy level, right? Because carbon has 1, 2, 3, 4 electrons in the second energy level. So after clearing that out, the fifth electron is in the first level, which is way closer to the nucleus and takes more energy. So to draw that out real quick, here's the nucleus, here's the first energy level, 1, 2, and then second energy level, forgive my drawing, 1, 2, 3, 4. All right, so the first 4 electrons are taken from the outside. They're more easily taken. And then the fifth one has to be taken from the inside, so it requires significantly more energy. Okay, why is there an increase between the second and third values, right? Second and third. So if this is first, second, and this is third, they're in the same energy level. So why should there be a difference? Because if I write out the configuration for it, right? It's 1s2. You don't have to write out the configuration. I'm just showing you to make something clear. The configuration for carbon is 1s2 and then 2s2, right? And then 2p2, right? You just walk your way through the periodic table to figure out the configuration. So if I take the first and second, that removes this. The third electron has to come out from the 2s sublevel. It doesn't want to. Why? Because the 2s sublevel is full. So it's particularly stable, and it's more difficult to remove that electron. Right, so here's the official answers. Right, the electrons in 2s2, not only are they more stable, they're also closer to the nucleus, and they experience a stronger electrostatic force of attraction, holding them in place. Okay, last question, I believe. Sketch a graph to show the expected pattern for the first 7 ionization energies of fluorine. Sketch the graph. You need your axes. First axis is ionization energy. Second axis is successive, like what number electron, right? 1, 2, 3, 4, 5, 6, 7. Then plot the first one. So the first 6 are going to come from the p sublevel, right? So there's 5 electrons in the p sublevel for fluorine, right? 1, 2, 3, 4, 5. So the first 2 are going to come out, right? First one, whatever dot you put. The second one is going to be slightly more. And now that I've removed 2 electrons, now I'm left with 3 electrons in the p sublevel. 3 is stable, right? Half full. So this increase is going to continue, but it's going to be a slight jump. Instead of being here, it's going to be a bit higher, right? Not much of a jump, but a little bit of a jump. And now the rest of the electrons in the 2p sublevel, they're just going to increase in energy at a consistent rate. Now 2p has been cleared out. The next electron has to come from 2s, which is slightly lower in energy, right? So because it's slightly lower in energy, that means it's going to require just a smidge more energy to remove that electron. So we draw that dot, we place it just a little bit higher, right? And then the 7th electron will continue to show the same pattern. So we see a regular increase overall, but there's a slight jump when you go from there's a slight jump whenever you're trying to take an electron from a full or half full orbital or sublevel. All right, that was that. All right, I'll see you guys in the next video.